Hi, my name is Jung Lee from Electronic Engineering Department. Today, I'm gonna give a presentation about SRAM device. And then, let me start my presentation. So, here is the outline. Before we take a look at SRAM device in detail, I think we have to understand about CMOS inverter more specifically. So, we are going to discuss about CMOS inverter layout, VTC graph, and about its margin. VTC graph, which is basic of butterfly curves in SRAM device, is very notable. In this part, I think understanding margin concept obviously is very important because the margin concept is also used in SRAM circuit, and the way how to make large margin is quite different between CMOS inverter and SRAM. So I think we must note about this. And then we're gonna take a look at SRAM device, very specifically discussing about basic operation and layout and SNM, which means margin concept in SRAM device. And further, we're gonna discuss about AT-SRAM and how people improve the small margin problem in SRAM. And lastly, width concept will be told. Finally, at the last, we're going to discuss about scaling down issue in SRAM device. So in this part, CPP and fin quantization concept will be told. So in here, you can see 3D view of CMOS inverter after contact etch. So the reason why I want to tell you about CMOS inverter first is actually SRAM device is comprised of two coupled inverter and two excess transistors, as you can see in this figure, I mean SRAM circuit. And also on the right side, you can see the layout of the SRAM device. So to understand SRAM device very well, we first have to understand CMOS inverter specifically. In this slide, you can see CMOS inverter circuit and its layout. By the way, do you know why there is difference between width of PMOS and NMOS? In this presentation, I'm gonna especially pay attention about width of each transistor. So, giving the answer first, the reason why there is different width is definitely to get symmetric characteristic of VTC graph. VTC graph is a kind of intersection graph of each NMOS and PMOS IV curves in CMOS inverter. So just by plotting the intersection points of PMOS and NMOS with varying input voltage, finally we could get VTC graph, which shows us the input-output characteristic of CMOS inverter. By the way, in the CMOS inverter, this kind of very symmetric curves of the VTC graph is not naturally formed. It is because there exists mobility difference between hole and electron. So if you can remember the IV equation of the NMOS and PMOS, I mean MOSFET, then current of MOSFET is function of mobility term. So to compensate this kind of difference from mobility, we have to take another solution. The solution is controlling width-length ratio of each transistor. So now let's see inverter layout again, which is in Chen-Min Ho's book. From this figure, now we can notice that the reason why there is difference between width of NMOS and PMOS is to compensate the difference from the transistors, each transistor's mobility. So now we can make a conclusion of part 1. In the CMOS inverter, to make symmetric characteristic of margin, we use geometrical solution. And so width ratio of PMOS and NMOS must around 2 to compensate for the mobility term. This is definitely how CMOS inverter control is margin. And as I told you before, margin concept will be also discussed in SRAM device, so we really have to remember definitely about margin. And also, as I told you in the outline, the way how to make larger margin is quite different between inverter and SRAM. Now, we are gonna discuss this detail of SRAM considering CMOS inverter, which we told until right before. And you can see 3D view of the interconnect structure of a CMOS SRAM cell. Here is SRAM device layout, and we can directly notice that there are some difference in widths of cascade, pull down, and pull up transistor. And also, in this case, it is very weird that width of pull down transistor is not smaller than pull up transistor, if you can remember the conventional CMOS inverter layout. I mean, obviously, we made conclusion of part 1 that width of pull-up transistor must larger than pull-down transistor to make large margin in conventional CMOS inverter. So we're gonna discuss about SRAM device, how SRAM device control its margin. Moreover, as there are 3 transistor widths in SRAM, so I'm gonna talk about each of 3 combination. This and this, this and this, and this and this. Totally 3 combinations can be made and 3 kind of concept will be also discussed together. This is one of the 3 combinations and beta ratio concept. Let's consider reading data 0 in SRAM and this node has data 0. Then we must make current flow to make voltage drop in bit line, which is already precharged. So that we can make current flow to this direction, we have to pay attention in this node. Even though this node has data 0, it must have very slightly small value of voltage potential to make desirable current flow from here to here. In other words, almost of the voltage drop must occur in this test gate transistor. So resistance, I mean pull down transistor must have much smaller resistance compared to pass gate transistor. If you can remember, transistor is compound word of trans and resistor, then you can notice that controlling resistance of MOSFET is equivalently same meaning of controlling IV characteristic. So we can adjust current characteristic of each transistor just by varying width of them, so that we can make high beta ratio, which definition is ratio of width length of pull down transistor and cascade transistor. So normally beta ratio must bigger than 1. And as you can see in this sentence, fin quantization is also appropriate solution under 22 nanometer node technology. This will be discussed later. Also, there is gamma ratio concept. If you understood perfectly about last slide, then this slide would be very easy. Let's assume we're gonna write data 1. We're gonna make this node from data 0 to 1. Then equivalently, it means we're gonna make this node data 1 to 0. Then just like last slide, so that we make desirable current flow and voltage drop, pull up transistor's resistance must far much larger than pass gate transistor. Then finally, we could get slightly small voltage potential value in this node. What we have to note in this slide is that we never have to adjust width length ratio between pull-up transistor and cascade transistor. It is because there is already exist different mobility between hole and electron. As you know, this is PMOS and this is NMOS. So if the width length ratio scheme is perfectly same in the SRAM cell layout, then gamma ratio can be naturally formed just like smaller than 1. Smaller than 1 specification is obviously what we wanted. And in final of the recombination, we're gonna talk about SNM parameter, which means merging concept in SRAM device. As you guys already know, SRAM is comprised of two coupled inverters, so VTC curves of each inverter can make butterfly curves, as you can see in this figure. In this case, we have to talk about width concept in SRAM, considering CMOS inverter. Obviously, in the CMOS inverter, we compensated the problem of small margin just by adjusting width of each transistor, but SRAM device does not. I think it is because to get appropriate value of beta ratio and gamma ratio, then inevitably butterfly curves of SRAM is naturally not perfect and symmetric because we didn't adjust width of pull-up and pull-down transistor in SRAM. So in the SRAM, we have to maximize the margin just by adjusting some more transistors. I mean like 7 transistor, 8 transistor, or even 10 transistor SRAM cell device can help making symmetric and larger SNM characteristic of SRAM. Of course, then now we can notice that there is a trade-off relationship between area and margin, which means quality of SRAM. So to improve it, I brought kind of paper which tells us effect of 80 SRAM. I mean effect of adding some more transistor to the conventional 60 SRAM. As you can see in this figure, just by adding 2 more transistor in here can help to improve margin of SRAM device, as you can see in here. The way how to improve margin is not controlling width of pull up and pull down transistors in SRAM. So just like CMOS inverter, but in the SRAM, just adding some more transistor can help the small margin phenomenon. And then let's make a conclusion about part 2. Considering beta and gamma ratio, the resistance of pull-down transistor must smaller than cascade transistor so that we can get higher beta ratio. And also resistance of cascade transistor must far much smaller than pull-up transistors so that we can make smaller gamma ratio. And let's note again that we didn't have to do much effort to make smaller gamma ratio because this kind of characteristic is naturally formed from different mobility between electron and hole. So from the resistance term, we can make this kind of conclusion. Pull-down transistor must have highest drive current value in the SRAM cell. I mean pull-down transistor must strongest in the SRAM cell. And cascade transistor must have intermediate strength. And finally, pull-up transistor must be weak among 3 transistors. And now my presentation will be ended just after simply discussing about scaling down issue in SRAM device. As you can see in this figure, as we approaching smaller node technology, the smaller CPP value is needed. CPP means contact poly pitch, and so it means distance from contact to contact in SRAM. So CPP value must be smaller, and moreover, even the size of the contact have to be smaller. So we have to make not only small size of gate length, but we really have to consider about sidewall spacer size and contact size. I mean CPP value as device scaling down. And this kind of graphs helps us to better understand about newest node technology. And so far, what made it possible to be very scaled nano-sized transistor? The answer is definitely downsizing of CPP value, as I told you right before of this slide. And also we can notice that 7 nanometer and 5 nanometer node technology is realized by Samsung and TSMC. And also CPP is sizing down together with development of node technology. And finally, fin structure. Under 22 nanometer node technology, fin structure is used by Intel in SRAM cell transistor. So after that, SRAM is very strong in area term to make high drive current. I mean just raising height of fin structure or adding some more channel could be very nice solution, which is called fin quantization. So under 22 nanometer node technology, multi-fin, I mean fin quantization is used in SRAM fabrication. In summary, we discussed about CMOS inverter and its width of pull-up and pull-down transistor and its margin. And in SRAM, we saw basic operation and width of pass gate, pull-up, pull-down transistor, and other parameters of SRAM. And in the final, we discussed about SRAM device scaling down issue, discussing about CPP and fin quantization. Thank you for your attention.